All right, in this video we're going to be reviewing three important vector calculus operations: the gradient, the divergence, and the curl. So before I start, I want to say that the important part for these three operations is not really their mathematical definition. You should certainly know how to compute it, but what's more important is that you understand the physical intuition behind each of these operations, because they're going to show up in your governing equations in fluid mechanics, in solid mechanics, and in heat transfer, and even more classes. And so it's important that you understand what they mean, so that you can better understand these uh, their equations. Okay, so let's start with the gradient. And so the gradient is kind of like an extension of the derivative. And so, the way that we understand derivative from calculus is that it computes a rate of change. The gradient just kind of does this in a multivariable setting. And so, when you have a function that's multiple variables, say a function that is a function of x and y, the gradient will take the rate of change in each direction, right? And so you can see here on the bottom left here, we have a function f. It's a function of both x and y. And so if we take the gradient, we take the rate of change in the x direction, and then we take the rate of change in the y direction, and we save that as a vector, okay? So one other important property for the gradient is that it returns a data structure that's n plus 1 in dimension. And so if you take the gradient of a scalar function, it returns a vector. But if you take the gradient of a vector function, then it returns a matrix. And so some examples of scalar functions could be, something like a temperature field. That's something you'll see in a heat transfer class. An example of a vector field will be something like velocity. And so as a physical example to kind of illustrate what the gradient is, what you're seeing here is a typical topological map of, let's say a mountain range, right? And so let's say that you're standing at the top of this mountain here, Mount Marcy, I think that's what it says, and you want to see what's the steepest direction. And so let's say that you have a marble and you want to roll it down and you want to see which direction is the fastest. Okay. What you can do is you can compute the gradient, and that's going to compute the rate of change of height in each direction, and then you can simply roll the marble down in the direction that has the highest gradient. Okay. All right, next we have divergence. And so divergence is an operator that acts specifically on a vector field, right? So this is a bit different than the gradient. So the gradient can act on both scalar and vector fields. Divergence can only act on vector fields. So think of like a velocity field, right? And so what the divergence physically expresses is, what I like to call how much the vector field either pushes in or pushes out. Okay, and so the exact definitions that you'll find in a textbook is that it measures the volume density of outward-inward flux at given points. And so let's say that we have a vector field. Here we have a 3D vector field, ux, uy, uz. All of them are functions of x, y, and z. And so when you take the divergence, and that's the symbol that we usually give for divergence. So we have the upside down triangle dot product with our vector, then you get this summation right here: partial ux, partial x, partial uy, partial y, partial uz, partial z. Okay. And the way that you can interpret that is that if your vector arrows are all pointing in at a certain location, then your divergence is going to be less than 0. But if your vector field is pointing outwards, then that's your divergence is going to be greater than 0. Okay? And so you'll see this most commonly in fluid mechanics to express conservation of mass. Right? And so as a physical example, let's say that you have a room and there's some hot spots and cold spots in a room. And so what we know from chemistry is that, when you heat air, it expands, and so expanded air will push outward. When you cool air, it'll contract and push inward. And so if you compute the divergence at each of these locations, in the hot spots, what you'll see is that, because the air is pushing outwards as it's expanding, the divergence will be greater than 0. In the cooler spot, since the air is pushing inwards, you'll get a divergence less than 0. But everywhere where the temperature is mostly stable, you'll see that mass is conserved and the divergence is equal to 0. And finally, we have the curl. And so very similar to the divergence, the curl is an operator that acts on a vector field. And so this is only for vectors. But instead of expressing how much the vector field pushes out or pushes in, the curl expresses how much it spins or circulates. Okay? And it's basically expressed as another vector field that shows the magnitude and the axis of the rotation. So mathematically, computing the curl is a little bit of a mess, and so it's a lot of computations you have to do. But I think the easiest way to kind of remember it is to take the divergence of this, take the determinant of this kind of make-up matrix right here. Okay, and so on the top row you have the unit vectors in the x, y, and z direction. I hat, j hat, k hat. And the second row, you have the partial derivatives, or with the partial derivative operators, okay, partial x, partial y, partial z. And in the bottom row, you have the components of your vector field, ux, uy, uz. Okay? And so if you take the determinant of that, then you end up with what's on the right, and that's going to be your curl. Okay? And so curl, I think most commonly you'll see it in fluid mechanics, in that it's used to quantify vortices or vortexes in fluid flow. That's something that's very important in aerodynamics. And so, if you have a vector field like this and it's spinning, then your curl is going to be, greater or less than 0. But, we also have a special case when the flow does not induce any rotation and we have a curl of 0. And in those situations, we call the flow irrotation. And so that's our review of gradient, divergence, and curl.